This is section 1 about sets. We've already met the set of natural numbers, and I'd like to show you some more examples of sets. There's quite a lot of notation and definitions and language around sets, so we're going to start with quite a lot of definitions and examples, but then later on we're going to move on to algebra of sets and how to build new sets. So let's start with some definitions and examples. We've met the natural numbers, and we've met the idea that numbers can be elements of the set of natural numbers. There's an important symbol for this. It's written like this, and it's pronounced x in the set S. So we write that if x is an element of the set. And there's a corresponding symbol, not an element of the set S. So we write perhaps x, and then this symbol S to mean x is not in S. Out loud I might say x is not in S, as a kind of shorthand for x is not an element of S. So examples, 3 is an element of the natural numbers. And I suppose at the moment we've only got the natural numbers, so my examples need to involve natural numbers, don't they? What can I say? The natural numbers themselves are not an element of the natural numbers. There's a distinction there. The elements and numbers, the set of all the natural numbers, is not itself one of the natural numbers. But perhaps you'd be more happy if I put a more obvious example like pi is not a natural number. My cat is not a natural number. Oh, sorry, not a natural number. My cat is not a natural number. Lots of things are not natural numbers, and we'll meet more of those later on. Okay, right, so we've got examples of things that might be a member of a set or not a member of a set. For most sets, this last thing is true, that the set itself is not an element of the set, and there's some discussion of that coming up at the end of this video. Right, so definition. We say that sets are equal if they have the same elements, and one way of saying this is that if x is an element of S, then x is an element of t, and the other way round. If x is an element of t, then x is an element of S. If you have both, then your sets are equal. So I'm going to write sort of a large if here. If both of these things, all of that, then S is equal to T. And maybe you can see why I haven't written it like that in the lecture notes. We've said they have the same elements. Later on we'll see something called the principle of double inclusion, which is phrased a bit more like this two-stage definition. Things in S need to be in T, and things in T need to be in S. That's what it means for sets to be equal. One very important set is the empty set. This is the set with no elements. So I suppose pi is not in the empty set, but also 3 is not in the empty set. My cat is not in the empty set. The natural numbers, the set of natural numbers is not in the empty set. It's not an element of the empty set. Nothing is an element of the empty set. In some sort of quite general sense, for all x, I don't really need to say what x is. Numbers, sets of numbers, whatever, x is not in the empty set. I haven't written it brilliantly there. There we go, fixed. This symbol is not to be confused with phi, the Greek letter, which is sometimes written like this or like this. So if your handwriting includes these symbols, then make sure that this one looks different, or select a different Greek letter if you're talking about an element of a set, to avoid confusion. The alternative, I suppose, would be to write something with curly braces. If you've seen sets can be written with curly braces, where you might have curly braces but then nothing to show inside, so you might just have a pair of curly braces. People don't normally like writing that pair of curly braces with nothing in between, so it's nice to have a symbol for it, perhaps a circle with a line through it, a bit like the Danish or Norwegian letter, O with a line through it. Right, okay, so that's the empty set, the set with no elements. It's one of the things I like about mathematicians is the ability to make something out of nothing. It has no elements, and yet we have an object, the empty set, which is in itself one object, the empty set, one thing on its own. it contains nothing, but it is something. Just something to think about. So we have another definition. We have subsets. We say that the set A is a subset of the set S if every element of A is an element of S. So we might say for all x in A, it is the case that x is in S, but not necessarily the other way round. They might not be equal. That's half of the definition, of course, of what it means for sets to be equal. The notation for this that I'm going to use is that A is a subset of S like this. My symbol has this line at the bottom. Beware, some people write A and then this symbol without the line at the bottom to mean this subset idea, that every element of A is an element of S. Okay, so watch out for that. And then related idea, you can maybe see where I'm going. Related idea is a proper subset where if A is a subset and it's not equal to S, then we say that A is a proper subset of S. And I don't have a go-to symbol for this. So beware, some people, actually I think including me, but some people write A and then this symbol again for this idea of a proper subset. So if you see that symbol, you don't know on its own whether that's one of the people who write that symbol for a subset or for a proper subset. Proper subset is a stronger idea. You also have this claim that A is not equal to S, that they're not equal. I suppose that means that there exists some element X that's in S but not in A. There's something else to it that means that those sets are not equal. So watch out for this. There is a notation that I've seen, maybe people might write A but then kind of crossing out the line at the bottom, a bit like a combination of a subset sign and a not equals to sign. If you have some notation for this, but it's probably best to spell it out, to use words like proper subset, which is why I'm showing you notation, but I'm also showing you definitions so that you know what to say. So I would read this: if A is a subset of S and A is not equal to S. That's what it means to be a proper subset. I should give you an example, shouldn't I? So we're going to see in a second how to build more sets, but let's say the set of even numbers from 0, 2, 4, 6, 8 and upwards. The set of even numbers is a proper subset of the set of natural numbers, because all of those even numbers are elements of the natural numbers. Remember to start at 0 and count upwards. All of those even numbers are elements of the natural numbers, but the sets are not equal. The natural numbers also includes things like 17 and actually all of the other odd numbers, but a single element would have been enough to demonstrate that they're not equal. Not all numbers are even. Let's move on. Okay, so here's that notation I just mentioned. People write curly braces with an unordered list inside of the elements that are in a set. So I have some examples here for the set containing the numbers 3 and 5, separated with commas, but held together with curly braces around the outside. That's notation that people use for a set. And this is used especially for finite sets. I'll have a definition of those in a moment. But also for infinite sets if there's a pattern to the elements. And that's quite vague, isn't it? But I've seen people write things like this to mean, you know, all of the even numbers, 0, 2 and 4 and upwards. I did this out loud a moment ago, set of even numbers and so on. So there might not be a last element, there isn't a last even number. It's probably best to say what you mean if you write out something like that, or to give a definition of which elements you're talking about. We will see those in a second. Now, importantly, the order of the elements inside the curly braces doesn't mean anything. And sets are considered equal, remember, if every element of the first one is in the second one and every element of the second one is in the first one. So these two sets, 3,5 in curly braces and 5,3 in curly braces, are considered equal because for each thing in this set, well, 3 and 5, and that's also in the second set, and vice versa, of course. So those sets are equal because equality is just defined by what your elements are and not the order. And also over here, repeating the elements doesn't mean anything extra. So this set contains 3, and it's written in there twice, but that doesn't mean anything. We still say that if I'm calling this set S, I still just say that 3 is in S. We don't have a concept of 3 is doubly in S or 3 is very much in S or something like that. We just say that 3 is an element of that set. If that's disappointing, if you have an application where you need repeated elements and you need to treat them as repeated, you're interested in how many times they're in your thing, then you might be interested in something called a multi-set. I haven't got any multi-sets in the lectures here, but that's an idea that has a name. And you might think that this looks quite clumsy to just, why would I ever list 2, 3, 3? Wouldn't I just list 2, 3? But we'll see later on that it can be tricky to tell if things are equal, and we shouldn't require people to always tidy up their notation to make sure that everything is only represented exactly once inside the curly braces. There are examples coming up where you'll have different expressions that actually describe the same number, but that's okay. It just means that that number really is in the set. The same amount as all of the other things in the set. It's in the set. It's an element. Okay, so repeating elements doesn't mean anything, and order of elements doesn't mean anything. I think it's my job to show you some confusing examples if I can. No, first, I should do some normal examples first. So we've mentioned that you might have a set defined by some property. We talked about the even numbers quite a bit. And a common way to write this is, well, curly braces to indicate that you're talking about some sort of set, and then x in S, you have some existing set S, some sort of wider collection of things, x in S, such that some property holds. And this property maybe depends on x, it's sometimes true and sometimes false. So this is a way of, if you like, filtering out some of the elements of S so that you're left with the ones that obey some property. I've got some examples of properties over on the next slide. Quick warning, some people do a vertical line. I'm going to try and be consistent and always write a little colon. Either way, you pronounce this such that. So you say x in the set S such that property holds for values of x, such that p holds. Let's look at some examples. So even numbers, I've mentioned a couple of times. You might write something out in words like this to describe the property. So here it's n is a natural number such that n is divisible by 2. That's fine. You might have some sort of equation or relationship in here. So n in the natural numbers such that n squared is negative. And this one is actually the empty set because there are no natural numbers with negative squares. So I could just write empty set for this example. And I suppose that challenge of working out what set of numbers am I talking about is not always straightforward. So it's not, you can't require people to always say this symbol if the thing they're talking about turns out to be the empty set. Other presentations of the empty set could be very complicated, and they might be equal to the empty set, and that can be quite challenging to discover. So just because it's got a complicated expression doesn't mean it's got any elements. And perhaps if you meet a complicated definition of a set, your first step might be to check whether it has any elements at all. For example, this set down here, where I'm trying to demonstrate that you might have multiple conditions separated by commas, the idea here is that you have to do all of the conditions to get a value of n into the set. So this is the set of natural numbers such that 3 divides n, and 5 divides n, and 7 divides n. When you meet a set like that, having just seen the previous example, a natural question is, does this set contain any elements at all? And in fact it does. You can find a number that is a multiple of 3 and 5 and 7. A good place to look is by multiplying together 3 and 5 and 7, which is 105. And in fact, I'm not going to prove it here, you should try and prove it. This set is precisely the numbers that are multiples of 105. So I could have written it like this in the bottom corner, but then it wouldn't have been a good example of multiple conditions separated by commas. It's always possible to replace that with a single condition and some and statements in between them, but it's common to see this with commas in between the separate conditions. Okay, right, hopefully those make sense. They're natural numbers, sets of natural numbers, and so far we've only seen natural numbers in sets, but I would like to put sets inside sets. I would like to talk about a set that contains objects which are themselves objects. So I need to move from just having sets that contain numbers to having sets that contain, well, perhaps a mix of numbers and sets and other things. This gets confusing quickly, so I want to start with a warning that in what follows we must not confuse any object A with the set containing A. So the set containing A is a different thing from A itself. For example, if A is the empty set, then A has no elements, that's what the empty set means, but the set containing A is a set with one element, the empty set. That's the empty set inside a pair of curly braces. If you like, the symbol in, like this, which counts, well no, so it detects elements of the set, that only looks one layer deep. It only looks inside the outmost set of curly braces. Here's some examples. All of these are designed to be confusing. So here we go. For example, let's look at B first. So B in the middle here is a set of sets. In this example, you can tell because of the two bits of curly braces. It's a set of sets, and in this case, 1 is not an element of B. And that seems confusing, right? Because I can see 1 here with a comma and some curly braces, but it's not an element of B because, well, B doesn't contain the number 1, it contains sets. It contains this set with 2 elements, it contains this set with 2 elements, it contains this set with 2 elements. It doesn't contain the number 1. If you like, that symbol in is a bit like the kids game Pass the Parcel. I don't know if you've played a game like this where kids sit in a row and there's a present, but it's been wrapped in lots of layers of wrapping paper, and the kids pass around the parcel, and each child removes one layer of wrapping paper, but only one layer of wrapping paper. So it gets smaller as it goes around, and eventually somebody gets whatever's in the middle. But this operator in symbol only removes one layer of wrapping paper. It only looks one level deep. So if you see the question, is 1 in the set B? Well, you're being asked whether, after you remove the curly braces, is any of the things that you see 1. This is a bit better than Pass the Parcel, isn't it? Because when you open the outer layer, you get 2 things inside. And I'm saying 2 things because B contains this set, it contains this set, and over here I can see another copy of the first set. Remember, repeats don't mean anything special. So B is just the set that contains, curly braces, curly braces, 1, 2, comma, and then the set containing 1 and 3. So V contains 2 sets, the set containing 1 and 2, and the set containing 1 and 3. Well, I've tried to pronounce those as if they're a single word. The set containing 1 and 2. It's a single object inside B. In fact, each of these sets has 2 elements. Let's look at A. So A contains a mix of numbers and sets. That's allowed. It contains, in fact, a set and a number. A is the set made of the set of all the natural numbers, comma, 3. So, in particular, 3 is an element of A, because there it is. It's one of the elements of A, separated with commas. But 4 is not an element of A. Sorry. I know that 4 is an element of the naturals, but the element symbol only looks one layer deep. So it just sees that that A contains 3, A contains 3, and A contains the set of all the natural numbers. So these are the true statements that 3 is in A, the natural numbers is in A, but in fact nothing else is an element of A. Those are its elements. If this is annoying, then you might like to think about unpacking or taking some sort of collection of all the things. So you might think about unpacking and joining together all the stuff that you get. So take the present away from all the kids passing it around, and just tear off all the wrapping paper and make a big pile of all the stuff that you get inside. And we'll get to that later, in a set theory sense. Anyway, so A has got 2 elements. I wrote this out so it's correct to write that the naturals is an element of A. It's not correct to write that the naturals is a subset of A. So you can't just do this on autopilot, always writing this symbol for numbers and this symbol for sets. Sorry. Because in this case, the naturals is just a plain element of the set A. If you're thinking of a subset is a set made of elements of A. So I could write, it's correct to write that the set containing the naturals on their own is a subset of A. That really is a subset of A. But I need to build this set containing elements of A. The fact that N itself is a set containing 17 and things like that is almost irrelevant to this exercise. That we're just trying to look at the elements of A. One of those happens to be, wow, my goodness, all of the natural numbers all at once. But that's almost irrelevant to the discussion. We've got to put it in curly braces if we want to build a subset of elements of A. Even though it's a set, fine. That set is not elements of A. It must be incorrect to write this because there are elements like 17, which is a member of this, but not a member of that. And subset means that every element of this should be in that. In particular, A is a finite set, and the naturals is not. We'll see finite sets later on. Okay, that just leaves C to talk about, and for C, I've tried to be maximally confusing by only using the empty set and curly braces. Maybe you're ready for this now. Reminder, the empty set is an object on its own. It happens to contain no elements, but for our purposes over here, we have object, the empty set, and we have the set containing the empty set. And we agreed on the previous slide, I think, that these are different. So this set really contains 2 things. This thing is not equal to this thing. Empty set is not the same as the set containing the empty set. Oh, not equal to. That's the second time I've forgotten to put a not equal to on. These are not equal because the thing on the left has no elements, and the thing on the right does have an element. The element is the empty set, but that's not an element on the left. The thing on the left has no elements. Okay, so those are 2 things that are not equal. So I wrote out that it is true that the empty set is an element of C. It's also true, and this is sort of a separate fact, that the empty set is a subset of C, the empty set is always a subset of any set S. The check for that is to check for all elements of the empty set, are they elements of C? And the answer is yes. The empty set has no elements, so I don't need to check anything at all. I'm done. Every element of the empty set does whatever you like. We'll see more facts like that later on. Some people call them vacuous truth when you have a sentence that starts for all elements of the empty set, because there aren't any elements in the empty set, so you're making a claim about nothing. Anyway, if you'd like an extra challenge, you could try to list all of the subsets of C. There are 4 of them, 3 proper subsets and this thing itself. So see if you can list the other 2 proper subsets of C. Hint, you'll need a lot of curly brackets. Okay, so those are my confusing examples. I hope they've confused you in a sense. And the main thing I want you to avoid is this idea that this symbol is for numbers and that one is for sets. This statement is just false on the right hand side. Okay, we've got some more sets that I'd like to introduce to you. We've got the set of integers, which is written with blackboard Z like this. In printed material, it looks like this. In handwriting, it's often more like that. Usually I do this because I don't trust myself to get the notation perfectly lined up like that. So I aim for that symbol. And that consists of all of the natural numbers that we had before, and then for everything except 0, a negative copy of those numbers with a minus sign out the front. Those are called the negative integers, -1, -2, -3, -4. And I'm not very proud of this definition, but I think for our purposes, we can say that those are positive integers with a minus sign written in front of them. That's not a complete definition because, of course, I need to tell you what that does. I need to tell you how to add together integers. You can add together integers, so I should tell you how to add 2 of these things together. And there's a definition for that to do with natural numbers. And I should probably also tell you how to multiply them. And the definition for multiplication uses the definition for addition on the integers. But none of that is particularly surprising because I think you've been working with negative numbers for many years now. So I'm going to show you these and show you the symbol for these, which is a blackboard Z, just like the blackboard N that we met for the natural numbers. And it includes negative numbers. Okay, still 0. I also want to show you the rational numbers, sometimes called rationals. The symbol for this is blackboard Q, which in handwriting nobody does anything like this. The general rule if you want to do one of these symbols is to do a regular capital, but with an extra line somewhere. So I do Q with an extra vertical line over there. That's the set of all fractions where the numerator and denominator are both integers and n is not allowed to be 0 or negative. I suppose I could say n in the naturals but not 0 because I'm ruling out all of those negative numbers we just had. This is quite close to a definition. The thing that I haven't captured is the idea that 3/6 and 1/2 are supposed to be equal. Those are different representations of the same number, 1/2 in words. We can do that, but we need something called an equivalence relation. That's coming up in one of the later videos that we'll see some technology for expressing the idea that these objects on the screen, although they're written with different numbers, 3 and 6 versus 1 and 2, a different pair of numbers, that they can represent the same number, halfway between 0 and 1. We'll see that later on, and then you might like to come back to this and try and understand, can I write down what it means for 2 fractions to be equal? Okay, So I should then also tell you how to add them and how to multiply them, but I'm really not going to do that here. Okay, so we also have the set of real numbers, which is written blackboard R, or sometimes I might write that like this, with an extra line on the left. That's the set of numbers with a decimal expansion, which I'm being quite vague about because these are going to be properly defined in the course Analysis 1, which is coming up very soon for prelim students at Oxford. And you need some technology here, especially if you want to talk about two real numbers with different decimal expansions that represent the same number. So actually the same challenge that we had before for rational numbers, where different representations mean the same value. The real numbers have that problem as well, and you need some technology just to write down what the equivalence is. So I'm going to cowardly leave this for the Analysis 1 course to define, but this contains, broadly speaking, all of the other rational and irrational numbers together, including things like pi and e and 1 over the square root of 2, or whatever you like, along the real number line, which is foreshadowing because the other set I want to show you is the set of complex numbers, which my symbol for these is a bit more like that, with my handwriting, C with a vertical line somewhere on it for complex numbers. You may have met these before. Either way, you will see more about them in the course Introduction to Complex Numbers, which happens at the start of first term. And these are written like this. So again, we have some notation, just like writing out fractions with a vertical line between them, or writing out decimal expansions, or writing out minus signs in front of something. We have some new notation. And here it's based on a pair of real numbers, but that also comes with some structure, which I haven't defined here. I should explain to you what it means to add together complex numbers, which I think you've probably met, and I should explain what it means to multiply complex numbers. I've put a little bit of that. There's the idea that I squared is minus 1, which you can either think of as a rule about I, or you can think of it as a rule about multiplication. That given two complex numbers, there's a rule for multiplying them together that gives you a complex number. A and B are real. Now, the hierarchy of these things is that I've been making the set larger each time. Each thing includes a new number. So the naturals are a subset of the integers. Let's write this out. The naturals are a subset of the integers. The integers are a subset of the rationals. If you believe that number divided by 1 means the same thing as the integer in the numerator, I think you probably do believe that, but it's a different notation. So again, you need some idea that those are identified with each other. Notation is subtly different from definition. Anyway, the rationals are a subset of the reals, because that includes all of the irrational numbers as well, like the square root of 2. And then the reals are a subset of the complex numbers if you believe that setting b equal to 0 gives you a real number. And I think I'm being pedantic now, but is a plus 0i a different representation of the same number that we need to set up an equivalence relation for? Probably not. Probably most people would accept a plus 0i definitely means a. There's definitely a copy of the real numbers there, even though the notation is subtly different. Plus 0i. Sometimes it still means something. Okay, right. So these are sets which you might have met before. Stacked together nicely like this. Okay, those are my examples of some common sets that you're going to meet. For the reals, we can also take subsets, and there are some special subsets that have their own notation that I want to show you now. So we have bounded intervals, and this is part of the real number line. Of course, remember a subset could be just any collection of elements that are in the reals. But for the reals, we have inequalities, and these come up so much that they've got their own notation. People write things like this. So a comma b in round brackets, not to be confused with curly brackets, which would be the set containing the elements a and b. I'm really sorry for that, but people use curly brackets for the set, and then round brackets for this idea. The real numbers between a and b, not including a and not including b. And then people use square brackets if they want to include the endpoints. So this notation, square bracket a comma b square bracket, means the real numbers between a and b, including both of the endpoints, so including a and including b. There is then, obviously, people would like to use a mix of those notations if they want to include one of the endpoints. So people write things like this, which makes me feel slightly uneasy because it's an open square bracket and a closed round bracket, but there you go. This is what people do to indicate an interval of the reals with one of the endpoints included. In my head, my mnemonic for this is that the round bracket has sort of rounded corners on there. There's something missing. It doesn't include the end value, whereas the square bracket goes right up to the edge and includes everything, and includes the number at the end point. That's just one of many silly mnemonics that I've got in my head to try and remember why this one doesn't include b and this one does include b. The square brackets feel slightly larger and more inclusive in my head. You're welcome to use that mnemonic if you like. These are bounded intervals because all the numbers are bounded by a and b, but there are also unbounded intervals if you only have a single inequality, and these come up quite a lot as well. So on the right here, I have just single inequalities compared to a single number a. We might be interested in the numbers x that are larger than a or less than a, and we might include a or not. And the notation for this includes this infinity symbol, which is like a sideways 8. And in the notation on the left, you'll notice that it might be here, it might be a negative infinity over here to indicate something similar to what we were just talking about, but this is really not the same thing as what we just had with. I really don't want you to go away and think that this is the same thing, but with b equals infinity, because infinity is not a real number. So the definition before, with those inequalities including infinity, doesn't carry over here. It doesn't mean anything to write x less than infinity. Is just rubbish. So this is, strictly speaking, this has got a different definition. But what does it mean to suddenly start writing sideways 8? And you'll notice that we never put square bracket to include infinity, because infinity is not a real number, so it's never included in these subsets. Okay, if in doubt, you might write out which inequality you mean, but quite often when you're reading somebody else's work or lecture notes or a book, you will see notation like this to say this is the set of numbers including a and no limit to how large they can be, or not including a and actually I want things less than a all the way down to minus infinity, not inclusive. That language is quite woolly, and if in doubt you might want to go back to these definitions. If you have two round brackets, so you're not including either endpoint, then that's called an open interval. And if you include both endpoints, or in the case of an infinite, an unbounded subset, if you include the endpoint which is a real number, then that's called a closed interval. So over here I have an example of a closed interval. That happens to be an unbounded closed interval. And over here I have an open interval that happens to be unbounded as well, but I could put minus 10 in here and everything's fine. And in the middle, I'm afraid this is neither closed nor open. But sadly, they're not opposites of each other, which is quite disappointing, I think. that the English words open and closed kind of mutually exclusive, I think. But we have sets here which we just defined, which don't fall into either of these buckets. So we have this case in the middle, if you like, which includes -1 and doesn't include 2. And you can use this notation if you find it helpful. If you're labeling part of the real number line, you might colour in points to mean that it's included, and leave it not coloured in somehow if it's not included. So this is some notation that's used for specific subsets of the reals, but reminder again here at the end of that bit that a subset of the reals doesn't have to be any of those examples. It could be all of the real numbers that are also natural numbers, which a subset doesn't fall into any of those cases. The words open and closed do have a nice generalization to other sets, and there's a course called topology in second year, which does quite a lot more with open and closed sets. That's something to look forward to, I suppose. Okay, just a few more. I've got the power set of A. That's the set of all subsets of A. So it is a set of sets. No funny business here. It's not a mix of sets and elements. It's just the set of all of the subsets. So that always includes the empty set, because the empty set is always a subset. Everything in the empty set is in your set, whatever you're thinking of. It always includes the set itself, because I'm not talking about proper subsets, I'm talking about all the subsets. And then almost always includes some other things as well. So notice here that I have to wrap this 0 in curly braces. I'm talking about the set that just contains 0. I think that sets that contain one element might be the most confusing. The set that contains no elements, I think you get used to the idea. It's got its own symbol. It's a kind of version of 0 in a way. It's emptiness. Hooray. Sets that contain lots of elements, you've seen examples of those before. I think the most confusing ones are sets that contain exactly one element, because the brackets look pointless. But the brackets are not pointless. The brackets are because I'm talking about a set. I'm talking about a subset of A. A subset of A is a set. So here are the proper non-empty subsets of this set, the set containing 0 and the set containing 1. Okay, and then I wanted to give you an example with the naturals. The power set there has many, many elements, including the set of all even numbers that I mentioned before, the set above, the set containing 0 and 1, the set of all primes such that p plus 2 is also prime, twin primes, if you know about those, the empty set, of course, and lots more things. So I couldn't list out all of the elements of the power set of the naturals for you. I'm sorry about that. Okay, this is an important idea because quite often I want to talk about subsets in general, and the natural home for the subsets is this power set, this collection of all of the subsets of a set A. If you like, the subsets are subsets of A, but they're elements of the power set of A. So if I want to talk about elements and membership, then I can look at the power set for membership of subsets within the power set of A. Okay, a little bit more notation, sorry. I want to tell you about Cartesian products, which is an ordered pair of elements. I'm doing this because we had unordered elements in a set earlier, and I thought maybe you might sometimes care about an ordered pair of elements. We had this along the way with pairs like the complex number definition had A and B, where you have to get them the right way around. The complex numbers are not equal when you swap their real and imaginary parts. So we have seen along the way this idea of an ordered pair. So in general, you can do the Cartesian product of two sets, even if they're not the same set, by taking pairs of elements like this, where A is an element of A, and the second thing here, B, is an element of B. And if those are different sets, then you can have these pairs which could be quite different. Key value pairs if you look at dictionaries in Python, if you do programming. But often we use the same set for each, and we're talking about pairs of real numbers or something like that. In which case we might write something like a squared for the Cartesian product of A and A. Cartesian product, you're supposed to think of Cartesian coordinates where the xy plane might be described as R2. In fact, that's my example here. It's important in the geometry course, and it is pronounced R2 rather than R squared quite often. You'll also meet three-dimensional space R3, where I should explain, that for R3, I'm crossing together three sets. I'm taking the Cartesian product of the reals, Cartesian product reals, Cartesian product reals a third time to make an ordered, and technically it's called an n-tuple with n equals 3, for an ordered set of three things in that case. But you get up to n different things. They don't have to be the same set, they often are the same set, in which case we might write this as a sort of exponent there, a power of n. And one apology here is that you'll notice that just within this video we've used this to mean both the open interval on the real number line and we've used this to mean a point in the set of A cross B. Sorry about that. So whether it's a pair of coordinates in a sort of what you might call a vector or something maybe, or whether it's an interval of the real number line is usually clear from context, whether I'm talking about this as some real numbers or whether I'm talking about this as some coordinates. But it is the same notation, and once again it's different from curly braces for a set. It's also different from square braces for a closed interval. There are lots of things that we might want to do with two numbers, and it's always tempting to put a comma between them and some sort of brackets around the outside and call it a day. If you've met, this is a tangent, but if you've met dot product of two vectors, then you might have met the notation where we take angle brackets around the outside. There's also a version in quantum mechanics where people put angle brackets around the outside and a sort of comma in the middle maybe. It's quite often that we have something involving two elements and we want to do something with both of them. It's maybe the most overloaded notation in mathematics, to put a comma between them and some brackets around the outside. Be careful out there. Right. Finally, I want to show you Russell's paradox as an example of what goes wrong if you're too generous with your definition of sets. If you take too many things to be sets. The paradox works like this. Suppose that you've got a huge collection of sets, loads of sets, as far as the eye can see, and you take precisely those sets which are not an element of themselves. That is all of the sets that we've seen so far in this video, sets that are not elements of themselves. Because, well, in that big world out there, a set could contain all sorts of things. The question is H itself in H? Is it an element of itself? If not, then it meets precisely the condition to be an element of this set. It does. S is not in S when S is equal to H. H is not in H. So it would be an element. It meets the conditions set out by the property. So it would have to be in this thing, which is called H. If it's not in H, then it's in H. And the other way around, if H is a member of H, then it must satisfy this property, which says that H is not in H. Oh dear. This is another contradiction. And it seems either way we have a contradiction. We don't know whether H is a member of this set or not. So H is neither in H nor not in H. And this is a problem if your definition is permissive enough to have any collection of stuff with anything written out like a property. If you like, the paradox comes from the idea that this has to define a set, being in the form of curly braces with a colon in the middle and some property over here. And the modern resolution is that that's too much, that you can't just take any property you like on any objects and get a set. We're not going to do any axiomatic set theory here. There's a Part B course in third year at Oxford that goes into modern axiomatic set theory, which shows you how to resolve this paradox by banning some things. Although I want to be clear, for our purposes, the thing that's banned is not the concept of sets containing sets. Everyone's okay with that, as far as I can tell, that sets are allowed to contain sets. So things like the power set, the set of all subsets, that's allowed. The thing that's banned is more subtle than that. So I'm afraid we do have to continue to deal with all of the examples I've shown you in this video of sets of sets, the difference between an element and the set containing that element. None of those are banned by Russell's paradox or the solution to Russell's paradox in modern mathematics. Well, thanks for watching the video and working through examples of lots of sets and things like that. In the next video, we're going to look at ways to make new sets out of the ones that you've got. We're going to look at something called an algebra of sets. So I'll see you in the next one.